Hey folks, how you doing? Don Grant, CTC Cutting Tool Counselor, with our first ever live video. Hopefully everything's going through fine. We're just gonna wait maybe just another minute. Looks like we got 29 people in the group right now. We'll just give it maybe another 30 seconds before we get started. We'll have a little banter back and forth. Um, kind of talk a little bit about the company Harvey Performance, just real quick before we jump in this. I got some really good information about this MRR triangle and to really help folks out there solve some problems at the spindle with end mills. I've been doing it for many years. I'm actually 37 years, started out making end mills back in the day, started in 1987. So hopefully I can give you some tips, some tricks that you can use in your shops to help you solve a lot of these end mill problems. And trust me, this is the method I use. It's the MRR triangle. And we're going to jump into that real soon here. Before we get started, again, thanks for joining us. Really appreciate it. We'll see how this goes. I told everybody it could be one of the best things you've ever seen on YouTube, or it could be a mess. But at any rate, I'm glad you're here. I'm glad you're watching it, and I'm glad you joined it. So Harvey Performance, if you're not familiar with us, many brands. I mean, everybody's probably familiar with Harvey Tool. Helical Solutions is another one of our brands. Micro 100, Core Hog, Titan USA. We have recently just joined forces with a company overseas, a European company. So ATA is now part of the Harvey Performance Group. I wanted to throw that in. They make SGS burrs, a lot of great products. And the reason I like to mention all of our products is because these methods that we use as application engineers and national application engineers kind of help us understand the cutting tools a little bit better, so we can help run through these procedures and processes to teach you how to run them better. So with that, let's talk about MRR. So let's jump into that real quick, and then we'll kind of start talking about it. Before we get started, again, before we jump into MRR, I just want everybody to know I'm going to be throwing out some prizes. We have a Google form that you can fill out if I announce you as a winner, which I'll just use your name tag on the YouTube live. There's a Google form you can fill out. We're going to give away, I'm going to give away some hats. I'm going to give away some polos. I'm going to give away some really cool swag here. We got some really nice hats. You don't get this hat. That's my hat. That hat's going nowhere. And besides, if I mail this hat to somebody, it's probably not going to survive. It's only got to stay right here. So nobody's getting this one. So we got some great giveaways. I'll give those with good comments, good questions. I'm going to save the polos for probably some really good questions at the end of this. So let's jump into MRR Triangle. So just to start this is a form that I built. So I want everybody to understand this on this, and I really want you to take things away from this that you can use in your shop. And you're going to be able to download this. We're actually going to put it on the In The Loupe page. You're going to be able to pull it off, and you can use it as a cheat sheet to help you dissect some of the problems that you actually have at your spindle. Now, MRR, let's just talk about MRR real quick, because it's very important. It's really kind of how we're judged when we're quoting jobs at the spindle, and we're trying to be most efficient. MRR stands for material removal rate. Forget about speed. Forget about how fast your machines are running. Forget about how slow your machines are running. It doesn't matter. What you're trying to do is establish a material removal rate, and how much material am I removing off of that to be efficient, so I can make my cycle time, so I can quote the job, be efficient, and get the work done the way we need. Now, MRR is a calculation. If you're not aware of this, it's a very simple calculation. It's inch per minute. Okay, that's our feed. This is how this works. Here's where the triangle comes from. It's inch per minute times your radial step over with your end mill, your radial step over times your axial depth. When you multiply those three things together, you get something called MRR, material removal rate. Now that material removal rate, like I said, are those three things. Those are the three things in the triangle. So the thing that we're going to teach, and the thing I want to explain to everybody in this, is all three of those things are connected to the failure of your tools. So what I mean by that is we get to play with those to fix any problem. And this is kind of something I kind of created, put it together in a teaching method because I use this at the spindle. We need to know what the MRR rate is, and then we need to fix the problems with the end mill by modifying these to get a better solution, more tool life, more efficiently for our tools. Okay. So now let's walk through this. Let's just talk about the MRR triangle here. I'm going to get comfortable now. So hopefully everybody's comfortable too as well. So the MRR triangle, like I said, is inch per minute times radial times axial. This is a sheet. It's all intertwined. One thing I want everybody to understand is once we run something with an end mill, we get a number, right? 1.34. Let's put that right in here. Let's say 1.34. Let's just say that's what we're running today is 1.34. I'm trying to walk through this. So all three of these things are kind of like, I was trying to think of an analogy today on how to use this. All three of these are kind of like a car. Think of a car. If I change the shocks on a car, it affects something else. If I change the tires on a car, it affects something else. If I change the engine on a car, it affects something else. By changing one thing, we have other things that are affected by that. That's why using this triangle, we can establish how much material removal we're using, and then take whatever the problem is and move it somewhere else. Let's give an example. Let's talk about this. Okay. So first of all, when you look at the triangle, inch per minute, radial and axial, those are the three things that make up your MRR. The big factor that we need to understand is this inch per minute is controlled by a diameter, a surface foot, a flute count, and an inch per tooth. I bring that up because that's a huge X factor. That has everything to do with this. Let me just show you how this works. If I change this to 7 flutes in this calculator, look at my MRR changes, right? Because it changes my inch per tooth, because 7 flutes is inch per tooth per. Let's go back up to 8 flutes, okay? So if I change my surface foot to 150, look at this. It changes my inch per tooth. It changes my MRR. If I change, or actually my inch per minute, don't get ahead of me. I'm trying to, if I change my inch per tooth, like let's say I want a thinner chip to 3 thou, it changes my inch per minute. Everything up here that changes my inch per minute affects my MRR. Then if I change my radial to 60 thou, my step over on my radial, and I hit enter, it changes my MRR. If I change my axial to 1 inch, it changes my MRR. The point I'm trying to make before we dive into using this to solve some of our problems is this whole thing is all connected. And it's all the reasons that an end mill fails at the spindle. So we got to figure out what is the biggest thing. And again, we're getting into my head, and you don't want to get into my head. I actually had a boss once that said, Don, there's always one crazy person in every shop. I could never find that guy. I could never find the crazy guy. So I don't know if it's true or not. But so the thing that we need to understand is all these are connected, right? So we can use all of these things to solve the problem at the spindle. Now I'm going to run through an example. Okay. We had an example. We were running 718 Inconel. We're running at a 31 thou radial depth of cut. We were running at 1.5 inches axial length of cut. It was 8 flutes. We're running 130 surface foot, and we were running 0.0045 inch per tooth. Inch per tooth is your feed. Obviously, your inch per tooth times your flute count gives you your inch per minute. Remember, that's what's counting for your MRR. This was not working. It was working okay for the customer, but we needed more tool life in actually it was 625 Inco. So I went in, took a look at the MRR triangle, and you said, you know what? This radial is causing some problems. Now, I'm going to take this number. I got this little cheat sheet up here, and you're going to be able to use this. I'm going to take this, and I'm going to put this right in here. This is what the customer was running. So he's running 1.35 cubic inches of material per minute. That's what he is. That's what he's running. That's what he quoted. That's what he's getting, not getting the tool life. So we look at this whole chart and we say, okay, the tool is chipping out. It's got a failure mode. Where do we think that's coming from? Well, I think it's coming from the radial. We thought the radial was an issue. So what we do right away is we say, you know what? We're going to go to a 2% radial. This is a high efficiency tool path. We're going to give everybody a chance to ask some questions and see if we can't use this. So we said, let's go to a 2% radial. Let's drop that down 0.0125. It's Inconel. We're about 2.5 times D. Light radial in super alloys works great. There's a tip. I'm telling you, don't be afraid to go to 2%, 3% in your super alloys on HEM or high efficiency machining. So we dropped that down. We dropped it down to 0.0125. Well, look at what it did to our MRR. It brings our MRR to 0.54%, which says we're not even close to being efficient. But this is where the MRR triangle comes into effect. Our radial came down and it affects everything else. So we looked at this and we said, okay, the axial, can't change it. Axial is a constant. It's in the program. Even if we could change it, I don't think we need to change the axial. It doesn't work. But when our radial comes down, guess what? We can start messing with the surface foot. Lower radial, less heat at the cutting edge, less heat at the cutting edge. We can bring the surface foot up. Remember, the failure mode on this tool was it was chipping out. It wasn't burning up. It was chipping out and it was failing because it was Inconel. So we brought this up to 200 surface foot. So then we went, okay, all right. And I'm doing this all behind the scenes. This is what I'm training. I'm doing this all behind the scenes. I said, okay. So I told the customer to drop down to a lighter radial. Not gonna let him be less efficient because you got to make rate. So I know I can bring my surface foot up. We brought the surface foot up to 200. We're still sticking with 8 flutes. There's something called radial chip thinning. The thinner the radial gets, the less you take on the radial, the higher the chip load can go. So then we brought the chip load up to 6.5. Okay. So now we brought the chip load up to 6.5. Now we're at a bogey of 1.19. So then we take this, we go 1.19, and we go there and we go, oh, wait, we're in the yellow. We're getting there. We're not as efficient as we were running before, but we're getting there. Now's where you can start playing with your surface foot and your inch per tooth because you have a light radial. So we can now bring this up and go, all right, well, let's see if we did 6.7. All right, now 1.23. Okay, so now we're at 1.23. What you're noticing when I'm punching this in here is I'm making very small incremental moves. If you notice with my inch per tooth, I'm going up tenths. And this is a 5/8 diameter tool. So I'm going up tenths. Well, now I'm at 1.23, very light radial, axial stayed constant. I'm at 65 inches a minute. Well, I need to get them over the edge. I'm just going to start a little bit, bringing up my surface foot a little bit, bringing up my radial. Well, we don't want to go that high. 13, that would be crushing it in Inconel, right? Bring that up, 1.31. We're at 1.31 right now. Remember when I said anything can happen? I just dropped my mouse. Hold on one sec. That's what happens when you don't have a lot of room in your office. So I just dropped the mouse. No big deal. So what you're doing is you're using this information in this chart to fix where the problem is, which in this case was the radial. Now we're at 1.37. So now I'm at 1.37. Watch this go green. So now this is before we even tested at the spindle. We run the tool. We literally go from 45 minutes of tool life to almost 2 hours of tool life. Why? Because the radial was causing us the problem. So we changed that. We modified the radial. We said, okay, looking at the tool failure point, we need to modify the radial. Well, if we modify the radial, that changes our MRR. Well, if that changes our MRR, what else can we change modify that will be less harmful, less harmful. You understand this? Because you got to understand a end mill is only new once. Car's only new once. A drill's only new once. And that's when you put it into the spindle. Once you put it into the spindle, then it starts wearing and you start having problems. So when this tool is in the spindle, it starts wearing. So we want to identify the biggest failure point. So in this case, it was the radial. We were able to get an extra hour and a half of tool life. We met the MRR by shifting the problem with the tool. So now you might say, well, Don, it's a nice sheet. I understand how this works. It's all connected. All this is connected. Even if I change the fluke count to 7, that's connected, right? If I change the surface foot to 200, it's connected. Diameter, even if we change the diameter, if we change the diameter over here, because we want to go with a smaller diameter, maybe there's some radius constraints, it's going to affect your MRR based on all the information. So it's our goal to figure out what's causing the biggest amount of problem and fix it. So what I did on this sheet that we're going to allow for everybody to use is you might be asking, well, how do I know where to go and where I should start to fix some of the MR or the material removal rate if I change something? Well, first, I made this little cheat sheet over here for everybody when they download it. So this is looking at chipping. If you're having chip rate, you might want to look at your feed rate and axial. And folks, understand something when I'm talking about this. I want everybody to understand this isn't a fix-all for everything. There's a lot of variables. There's a lot of variables. There's tool holders. There's machines. I'm not making excuses. Trust me, I'm not making excuses. I've seen it all. There's tool holders. There's machines. There's rigidity of the fixturing. There's coolant concentration. There's machine tools. Depends if you're running a Fadal, a Makino, a Hermla. All machines and holders bring in variables. That's what we're trying. So if we're looking at chipping, you got feed rate and axial. If you're looking at breakage, you got axial and radial. This is a cheat sheet for what you need to look at. Excessive wear, you got surface foot, coolant, built up edge, fluke count. There's a big one. You got fluke count, poor surface finish. That could go to diameter, run out, and fluke count. So also what I put on the sheet is another nice little cheat over here. This is an MRR cheat that I want to explain to everybody. So let's say that you think the radial is having a problem, and we did that. We had 0.0315 is where the radial was, and we want to drop that radial down to 0.0125, right? If you go to this radial button over here and you say you bring the radial down, it's going to highlight your radial and tell you what you can move. Okay, remember how everything's connected. This is how this is connected. So if we bring the radial down to a point where we think that's what's causing the problem, like let's say if we look at chipping, feed rate, axial, feed rate, breakage, axial and radial. So we bring this radial down, it's going to tell us that we can bring our surface foot up, we can bring our inch per tooth up, and we can bring our axial up. If you go the opposite way, and let's say we want to bring our radial up. So even if you're working within this, and we go 0.060, and I apologize for anybody that is hopefully on the meeting that might be from a European. Like I said, we have a European company. I'm doing everything an inch. Appreciate that. So if you bring your radial up, now you need to bring your axial down. You need to bring your inch per tooth down. You need to bring your surface foot down. Okay. Philip actually has a question. How do you consistently manufacture K-land grinds on your Walters? I like going right on a curveball right away. How do we consistently manufacture K-lands on our Walter grinders? Well, because I'm not in the manufacturing, but the Walter grinder software, Tool Studio software, just to answer your question, is very intuitive. A K-land is a lot different than a hone for people out there, and I'm sure you're aware of that too, Philip. A K-land and a hone are two different things. A hone is not done in the Walters. A K-land is done in the Walters. We do have tools that have K-lands on them. We consistently do it by using rigidity and holding, great software, and running them that way. So we do maintain really good K-lands on our HXVR series. So hopefully that answers your questions as far as that goes. So same thing, if you look at the radial, axial, and all this information, all this is connected. So this is a little cheat for everybody to kind of use to, if you're going up with your axial, right? Here's your axial. If you go up with your axial, well, you better go down with the radial, or you better start looking at going down with the radial to solve some of these problems. But when you go down with the radial, you can go up with your surface foot, and you can go up with the inch per tooth. Okay. Diameter. If you go up with the diameter, this is the same thing, and highlight. So if you go up with the diameter, we now know that we can play with the radial. We now know that we can play with the axial, and we can also play with the inch per tooth. So these are what are solving these problems as you're running through this MRR triangle. Surface foot, same thing. We know surface foot has a lot to do with heat, right? So once you start playing with the surface foot, you're starting to mess with heat. One thing that helps heat when surface foot goes up is your radial step over. You want to start bringing your radial step over down when your surface foot goes up, but when your radial goes down, your inch per tooth can go up. We have another question from Paul. Ideally, as a rule of thumb, do you follow the cheat and that top to bottom order? First thing I'm kind of doing in a rule of thumb is, so we're kind of I don't want to say skipping a couple steps, but the first thing you want to do when you're starting a job is pick out the right tool, right? The right flute count, the right geometry, the right coating, the right length of cut, and everything else. And that's all based, Paul, based on your tool path, right? Everything's based on a tool path. What kind of tool path are you running? Are you running a traditional tool path where your radial is going to be really heavy, let's say 120, and then your axial is going to be really light? Maybe your axial is at, ½ inch. I mean, are you running a traditional tool path? Are you running a high efficiency tool path where your radial is going to be on the light end, where you're 0.0125, and then this is going to be 1.5 inches? So using that as a rule of thumb, you put the right tool in, and then you make modifications based on the wear of the tool, where you're trying to get life. And this is at the life of the tool. So Paul, if you put in a tool right away and it breaks, I'm a huge, I always say this every time I do some training. Really, the number one goal, and don't get me wrong, I'm an application engineer. I've been doing this for many years, but really our number one goal when we put a tool in the spindle is not to get that tool to break, right? Come on, let's be honest. We're all in this meeting. We're all adults. You don't want that tool to break. Now, we have enough evidence to say that, hey, if we start these speeds and feeds in this material, it shouldn't break at an 85% success rate. But you have to start there. You have to start with, okay, I'm going to use known speeds and feeds. We're going to put this in here. We don't want this tool to break. Now, when you start running that tool, you start getting this MRR and you start establishing what that tool life is versus your cost per part, right? That's why I get called in. I'm a national application engineer. Trust me, this is not my real job. My real job is actually going to the spindle and fixing problems at the spindle by working with the customers, such as yourself, Paul, by just going, okay, so we got a tool, we're making parts, everything's good, we just want more tool life. That's where this tool comes in, right? We want to say, okay, what is the failure mode of that tool at end of life? And how do we prolong that tool? It could even be changing the geometry on the tool, right? We could be going with a different series tool. We could be adding flutes. We could be adding a coating. Maybe if we're running dry, we put coolant in there. There's a lot of factors that we can do, but this MRR we can use as a starting point because we're all starting here. You put it in, just like I said, you're putting the tool in to get it not to break. Well, when you establish that, you establish your MRR. What I would tell you is when you start and you start evaluating whether you want to improve the tool is figure out that number. Just write down on a piece of paper, write it on a computer, and say, what is my current MRR and my tool life, right? Let's say that tool is lasting an hour, and I'm running 1.36 MRR. There's two numbers. There's two variables now that you can play with this end mill. We can play with this end mill until you figure out how to get more life, out of that tool and more MRR. And that's what you're trying to establish. Now, there becomes a point where you can't get any more. And that's when you start messing with the flute count. You start messing with different tools, different strategies. I'm a big proponent of making sure the tool path matches the tool. Putting the right tool in the tool path is really going to solve a lot of your problems. Here's a perfect example. You wouldn't take a NASCAR, if there's any NASCAR, and you wouldn't put it on a drag strip. It just doesn't work. That car is not built to go on a drag strip. You wouldn't take a drag car that's way faster than a NASCAR, and you wouldn't put it on a circle track. It's not built for that. So having the right tool in the right situation really helps solve those problems. All right, so I'm going to give away a hat here real quick. Who wants to say? Let's see, give away a hat. The first person, Helical Solutions. If you use any Helical Solutions, the first person that can tell me the two coatings that Helical has for steel and ferrous materials, the first person that can put in the comment, I'm going to give a nice, actually, I'm going to give a nice Helical hat. T plus A plus. Yeah, nice. We got a lot of good comments. Phil's got it. Phil's got it right. Mitch Toftel's the first one, but Mitch works for the company, so I'm going to disqualify you, Mitch, right away. So it looks like Philip, yep, Philip is T plus, and what's the other one? A plus. Yeah, sorry, Mitch, can't do it. See, we got a great number of application engineers throughout the country too. So this is really good if you need some special support. All of our application engineers are well versed in these type of techniques and can help at the spindle too as well. And understand something for everybody that's on this call. And it looks like we got 70 people. Thanks for the 13 thumbs up. Really appreciate that. And again, this is our first go around on this. So want to really make sure you understand these. So we have a question that's from David. And it just went away a little bit. Let's see. David says, does your MRR triangle work for micro machining, less than 1/100 thou diameter, or are there modifications one should make? That's a great question, because I was thinking about this, because we had this question. We did a little trial run before. We had this question before. And here's the thing. When you're talking about micro machining, I love micro machining. If you haven't had a chance, go to In The Loupe. I did a little blurb, a little video, a little plug on micro machining. It has a lot of good information there. When you're dealing with micro machining, boy, is the first thing you're trying to do is get the tool not to break. Okay. That's a great question too as well. And I think we're going to send you a hat just for that, David. Would you like a Harvey hat, or would you like a helical hat? Not to get off the subject. So your goal is to get it not to break, but everything that you see in the MRR triangle applies to all cutting tools, because it's these three things on an end mill: inch per tooth, radial, and axial. Now your radial on a miniature tool is going to be very light, right? Your axial, your pressure that's on the tool, your deflection amount that's on the tool on a miniature tool is going to be a lot different, but it all applies the same way. So David, absolutely 100% this applies for miniature tools. You can use it. And if you have an example, we can actually take a look at one of those examples. If anybody has an example on here, or something that they're using currently that they want us to walk through with this MRR triangle, I'd be more than happy to give it. That's what this is all about. Mitch with the hats. I'm telling you, Mitch, can somebody block Mitch Toftel? That would be great. He's our Southern California rep out there. But you'll get a hat, Mitch. There's no problem. We'll make sure we send a hat. But the MRR triangle, the thing that we're really trying to establish here is MRR is how we're judged. It's cubic inches per minute that are being removed. We shouldn't be looking at a machine and the aspect of speed, how fast it's running, how slow it's running, how much it's moving around. We should determine how many cubic inches of material are we removing per minute. What's our tool life? And then that's what those factors are that we want to judge against. Split the hat, the next right answer. Nice. Anybody else have any questions on the MRR triangle? We can do a couple more examples on this. Let's do an example as far as let's say we just got a 5 flute end mill. Okay, we're taking a radial. We'll call it a 1/2 inch diameter. It's pretty standard. Let's do a 30 thou radial because we're going to do HEM. Now we don't want to exceed this more than an inch. Here's a good general rule that I want to give out to everybody right here is really when you're doing high efficiency machining, all of your axial should probably not exceed 2.5 times the diameter. 2 to 2.5 times the diameter, because then we start getting too much deflection and we start having poor surface finish. That's where I have diameter in here. And we have to start bringing up the flute count. So be mindful, whatever your tool is, try to stick within 2 times the diameter of that tool. Just reading some of the questions. Where do we get this majestic MRR triangle spreadsheet? This will be posted on our In The Loupe page. You'll be able to download it right from there. We're going to put it in there. The only reason it's not on there now is because I'm kind of using it to move things around. And I want to lock the sheet so people don't have problems with the formulas that are in there. So this will be on the In The Loupe. That's a great question, and look for it within a day on there and download it. And if you don't see it, just send an email in and we'll make sure we get you a copy of it. Is there a sanity check for a percent of change, i.e. the surface foot versus inch per tooth? Well, your inch per tooth is going to be, well, that's a great question, Paul. That's a great question. And that's all contingent on radial. When you mention surface foot and inch per tooth, I think radial right away. My brain's going to radial. When you're starting to mess with your inch per tooth and your surface foot, you're looking at your radial, because the lighter the radial, the higher you can go on the surface foot, the lighter the radial. Now, let's not get carried away. I'm gonna say it. You guys, everybody's on here. We got 74 people. I'm gonna say it. Just because we're running high efficiency tool paths and we're making light radials does not mean we can start getting crazy with the surface foots. Okay, I've been doing this for 37 years. Be mindful of the surface foot. Surface foot is heat. Okay, but what I'm telling you, this is a perfect example. And Paul, great question, because if we start jacking this up, okay, because we want to get the MRR. Let's go to 500 surface foot. Look at the MRR is going up, man. We're going to go to 600 surface foot. Look at this. Look at my MRR is going crazy. What I'm telling everybody on here is let's keep this down, okay? Let's keep that surface foot because it's heat. It's going to destroy your cutting tool. And let's start bringing up some of these other things. Let's start bringing this up, right? Let's start bringing this. Let's start bringing our diameter. Let's start, if we can, 25. Let's start bringing our axial a little bit. Let's start using some of these other tools and keep our surface foot a little bit at a modest level. I think that we've added, as an industry, don't get me wrong, 2% radials, light radials, you can bring that surface foot up, but we don't need to be, in my opinion, running Inconel 718 at 500 surface foot. We still need to be down in that range of 130 to 200, depending if you're running a high efficiency tool path. We do have a couple more questions here. So I'm going to say I do, this is from Matt. I do most stuff in freedom units, but moving more into metric. Good for you. I'm glad you're moving into metric. I still won't make the plunge, and I'm getting old enough. I hope the spreadsheet does both at the same time. You know what? That's a great question, Matt, and I think I'll make sure that it does. How about that? We'll convert it and put metric in there, because I do think this is a great tool. And when I say I do think it's a great tool, this is a tool that I use on a regular basis, and of which that we wanted to make sure that we teach on it. Sanity check for percent of change, i.e. Paul. Okay, I'm just kind of reading through some of the questions because I want to make sure I get to everybody's question here. How do you determine your initial MRR target? That's a great question. That's a great question, because where you're going to determine your first MRR target is basically going to be on your recommended speeds and feeds from the manufacturer for what you're doing, right? Because everybody has recommended speeds and feeds. So you're going to want to find out what the recommended speeds and feeds are. You're going to put that tool in the spindle. Those recommended speeds and feeds are going to get your tool not to break. I can't speak for everybody, but I'm speaking for us. This is our In The Loupe, right? Harvey Performance. So those speeds and feeds are going to get you not to break. And then what you're going to do is you're going to monitor that tool life and see where you're at to what you quoted, and then make your modifications. So your goal MRR that you're shooting for are usually going to be manufacturer recommended speeds and feeds. Okay. Now those two numbers vary, right? They vary from production to prototype. As a machinist, had my own shop for 10 years. Production is run a lot different than prototype. If you're running production, you probably want to be using this to get the most out of your end mills. You probably want to be looking at your holders. You want to be looking at everything to get the majority out of your end mills. So that's kind of how you want to do that. Hopefully that answered your question. Let me see. How do you tackle area facing with low axial? Man, I hate facing with an end mill with low axial because a lot of things change. Low surface foot and high radial. Absolutely. That's what you're doing. Hard to deal with low feed rates. So you're right. I like higher flute count in that when you're facing on the tool. I try not to exceed roughly 10% of that diameter when you're facing on that. You can do it one of two ways. You can face traditionally. That was Jonathan, I think. Yep. Jonathan, you can face traditionally, which means here's a little tip for you, and that's a great question, is if you have a thin floor and you're getting warpage in that floor, try using a high efficiency tool path with a light axial. That will help dissipate some of the heat, and you won't get as much warpage. So even though you think you're doing a light facing and you want to just do a traditional path, if your floor is very thin and you're getting some warpage, try and do a trachoidal or a high efficiency tool path even on the floor. But if you're doing that, I like a higher flute count, usually 6 flutes up to about 3/4 of an inch in diameter. And then you take a heavier radial, probably 60, 70%, and then face your floor. Just be careful with how much material you're actually taking off. Let's see what other questions we have. How do you take areas of face and low axial? We've got that. Trevor says, I can definitely see myself using this tool to teach MR to my current and future apprentices. It is a great tool, Trevor. I'm telling you, this is one of the things that I don't struggle with teaching it because it's a method that everybody is using today. Everybody's using this. They just don't understand it. I mean, when they're making changes at their spindle, they're making these changes to try and get more tool life. They just don't really understand how it all comes together and how you need to change that. But when you get a bogey MRR and you know what that MRR is and you want to make your tool run better, you need to know what you can change to get your tool to run better. And that's exactly what this cheat helps you do. Sorry, did you say that you are sharing this tool? Yes, we are. We are sharing this tool. Everybody will have access to this. Like somebody had mentioned before, I really do want to make it for metrics so everybody can use it. Like I said, we are a global company. Harvey Performance is a global company now, and we're proud of it. So we have companies overseas in Ireland and Europe and England and everything else. So I need to jump on the metric bandwagon more than I have. So this will be shared for everybody. To make sure I understand your target and feed and speeds recommended by the tool manufacturer, and try not to overload the tool by keeping your MRR value below 2 times of your axial diameter. Okay, to make sure you understand, if you're running HEM, high efficiency tool path, I'm just talking about high efficiency, dynamic milling, Mastercam, profit milling, Esprit, volume mill, all those dynamic tool paths that take a low radial. Now we're down into 30 thous. Okay, all those dynamic tool paths, you want to try not to exceed 2 times the diameter. Here we go, for maximum speeds and feeds. Deflection is a killer with an end mill. It's definitely a killer when the tools get smaller. But as we start sticking out of the holder more, the deflection gets greater. And we really need to stay within 2.5 times of the diameter. Obviously 625, we're 1.25 inches, ½ inch. you know, you don't want to exceed 1 inch diameter. Now, does that mean if you go 1.25? Yeah, but here's a caveat. Here's a caveat. Let's say that you're in a 1/2 inch diameter. Let's just say, let's throw this out there. You're on a 1/2 inch diameter and you have to go 1.5 inches. You have to. Remember, axial is going to be a usually common. You have to go 1.5 inches. Use your radial. Remember, if we said axial goes up, let's look at that. Look at that. Radial goes down. You see the red on there? So I'm saying if your axial goes up, right here with this cheat, your radial better go down. But as your radial goes down, your surface foot can come up and your inch per tooth can come up because we have something called chip thinning. A question from somebody that couldn't sign in. What would you suggest for an axial depth of cut while slotting with a 10 thou diameter M mill and nitinol at 60? These are great questions. Axial depth of cut for a 10 thou diameter, Reese, probably about 2 thou axial. Now I'm going to tell you something. This is a great question because Reese, you led me into something here. When you are slotting with a miniature end mill, you want to do two things. You want to take a light axial depth. You're going to have to, and you want to put as many flutes as possible in that tool because you're not slotting traditionally. You're making a slot. So your axials are going to be 1 to 2 thou. You're going to add as many flutes as you can. And here we go for a question. Why for a Harvey hat? Here's the question. Nobody that works for the company. Why do you want to add as many flutes on a miniature tool as you can? What's the point of adding a lot of flutes? Whoever can answer that is going to get a Harvey hat. Bigger core. There you go. Swiss machinist. Bingo. Bigger core. But usually in a traditional slot, if you go with a bigger core and add flutes, you can't get the chips out. But I just said you're taking very light axial depths. So if you're taking light depths of cut, your chips are not necessarily the problem. And if your chips aren't the problem, between you and me, load as many flutes as you can into that end mill. And Harvey goes 5 flutes down to 10 thou. So that was a great question, Reese. Thanks for bringing that up. Sliding with miniature tools has been a huge problem. And the way I solve them, 2 things. Lots of flutes and oversized shank. There you go. That's the tip. There's the tip. If you're running miniature tools and you're struggling with them breaking, go with as many flutes as you can and put them on an oversized shank. When I say oversized shank, we have 1/4 inch, larger diameter. They normally come on 1/8, 3 millimeter shanks. If you can go with an oversized shank, you will see your tool life double, triple. Disclaimer, maybe even 10 times tool life. It's really good when you do that. Luke's Laboratory. I'm a mechanical engineer. Law of cues for stiffness is a big deal. I started a business to make cool 3D printing parts, and to that end, I now need to be a machinist. I now need to be a machinist too. These are good tips that you're going to want this. You're going to want this to actually use to help you get through this. This is a great tool. I'm telling you, that's why we were kind of excited as Harvey Performance to kind of get this out there and just say, listen, I'm a big proponent of, you know, give a person a fish, feed them for a day, teach a person to fish, feed them for a lifetime. So this is kind of our part to help support the industry. Same thing with the In The Loupe. If you haven't subscribed to In The Loupe, please do. We appreciate it. It's great content. It helps me actually support the rest of the cutting tool industry. I was just appreciating all the help in the chat too. Well, you are most welcome, Luke's Laboratory. We got to send Luke's Laboratory something. We got to make sure we get him a couple hats out there. So I'm letting the moderators know that Luke's Laboratory is going to get a couple hats. We'll send you a couple Harvey hats and a couple Valor drill hats too as well, as far as that goes. Reese, thanks, Don. That question came up from your favorite Lisa. Lisa, yeah, Lisa Bailey up in Minnesota. Great. I have so many friends, Reese. I'm glad you bring that up. Hopefully they're on this. They're probably making fun of me at this point, but I have so many friends in the industry, and I am truly here to kind of support and move our industry to the next level. And I think moving it to the next level is bringing things like this that is different than what the industry is kind of used to. It's like we all know that we need to move either our axial, we know we need to slow the tool down, we need to take less radial, right? We all know this. We can bring our RPM up, we can bring our RPM down. This is not something that I'm teaching today to basically say that we don't know this as machinists. But I think what we don't know is we don't know how it all affects each other. We don't know how it all moves, and we don't have anything that gives us a cheat that we can in the next generation teach our new machinists to say, hey, this is how it works. I didn't know this when I was starting out, right? I knew how to move things, but I didn't know where I needed to go with this. You have an advantage and you can use this. And this isn't artificial intelligence either. This is Don intelligence, which is not very, very high up on a chain. Let's see, you guys come recommended from a local machinist friend who's done some parts for me. Great. I mean, word of mouth is the best. I mean, Harvey Performance has a great reputation in the industry. We're there to help and support. We got some team members on this chat right here that wanted to jump in to help answer some questions. Reese Trotter, Mitch Toftel. I know there's some other team members that are actually on here too. We got some great marketing people on here that are supporting, want to help spread this word out. They're actually doing all the logistics on this. We got a great machinist team. Our manufacturing facilities are state of the art, and we really enjoy doing this and supporting the machinists out there. Shout out to the Machining Advisor Pro by Harvey Tools. All right, let's talk about the Machining Advisor Pro. That's awesome. Hey, Zach Ney, an old friend out there. I see Zach Ney. Amazing tool, Don. Yeah, that's great. Zach's a good friend out in the Seattle area. So I mean, it's great to see familiar names. It's really good. So Machining Advisor Pro, we do have a great tool. It's called Machining Advisor Pro. It's MAP. This is what's great about MAP. This is when somebody was asking before, how do you know where to establish your MRR? What I should have said is by using MAP, Machining Advisor Pro, it takes any one of our tools in any one of the catalogs, Valor, which is our drill, Harvey tool, and Helical. You put it in and it'll give you recommended speeds and feeds. It'll give you recommended axial depths. It'll give you recommended radial step overs. It'll give you all this information that you can start with your MRR, and then it's your job to figure out whether that meets your requirements, whether you want to get more life out of that tool, whether you want to run faster, right? We can run faster. But don't get confused. When I say faster, I mean, let's not think after this, if you're on this training, let's not think of faster as far as how fast the tool's moving. Let's start thinking in terms of how many cubic inches was I removing and how many cubic inches per minute am I removing now. That's the point of this. We don't need to run faster. What we need to do is find out what's causing our tools the biggest amount of problems and adjust them into a situation where they like it and they work better without having to. Here's my sales pitch. All right, you're going to get it. My sales pitch. I've gone into so many customers that'll have 5 different brands of cutting tools on a table, and mine being one, and they're saying, man, this tool is chipping out on the edge. Well, what is that one doing? What's chipping out? That one? It's chipping out. I'm guessing the other, you don't have to tell me. The other 2 are chipping out too? Well, maybe this isn't a tool problem. Maybe this is an application problem. And we got to address the application, not the tool. That's not saying that one tool might run a little bit better than the other, but we got to start looking in terms of fixing the application, not just changing out tools. Let's see. I'm interested in becoming an application engineer like yourself. What should I do to help towards that goal? Thanks for the info. Learn, soak it up, mentors. I have so many mentors in this industry. Man, I can't thank them all. Soak up as much information. Think outside the box. Try things. This is how I tell everybody. Everybody goes, man, you're so good at running cutting tools. How did you learn? Well, break a lot of cutting tools. And then I had my own business for 10 years. So I broke a lot of cutting tools and I paid for a lot of cutting tools. You'll learn how to use them. Breaking cutting tools and failing is the first step to learning. Honestly, you have mentors, they tell you to do something. So if you want to get in this industry, learn as much as you can. Think about it differently. I'm a big proponent of, cutting tool industry's not been stagnant for years, but we do regurgitate a lot of the similar things that we used to do in the 80s and 90s. Yeah, I said 80s. I'm that old. Why do you think I wear a hat? I have no hair. So no, I do have hair. Don't think I don't have any hair. But we regurgitate things that we know as the norm. But the thing is, the machines aren't the norm. The tool paths aren't the norm. The holders aren't the norm. Everything has changed. So we got to start looking at some of this stuff in different aspects. That's why I use this MRR triangle. I have to be more efficient. Any additional tricks? Helical high feed mills. High feed mills, that's good. So a high feed mill, if anybody's not aware of what a high feed mill is, a high feed mill cuts on the bottom. There's like 2 radiuses on the bottom of a cutter, and it only cuts on the bottom. So you can only take light axial depths of cut when you're using a high feed mill. Now, a couple tips and tricks with high feed mills. Number one is I would never recommend anybody using a high feed mill unless an end mill is just not doing it. Because an end mill is going to be a lot more efficient. A standard end mill that cuts up the side is going to be a lot more efficient than a high feed mill. That being said, we actually put high feed geometry on an end mill. So you get high feed geometry on the bottom, but you can still use it as an end mill. So that case, it would be a lot more efficient. They run a lot faster on the inch per tooth because there's a lot more chip thinning. But don't get confused. Faster does not always equate to MRR. Where a high feed mill comes in, where you would use a high feed mill, is if you're going down in a deep pocket and that end mill is just too much deflection, too much force on the radial, the side, too much of this radial force, that tool is deflection and it's breaking. If that tool is deflecting, and you can't get through it, you want to look at a high feed mill to actually get a feature that you can't get with a standard end mill. The MRR is material removal per minute inch cubed. Yes, inches, cubic inches per minute. That's what it is, cubic inches per minute. So right here with these parameters, we have 3.09 cubic inches per minute being removed from our material. That's what it is, absolutely. Reese, again, this MRR sheet calculation for cubic inches per. Okay, thanks, Reese. Thanks for answering that. Appreciate that. Reese is one of our technical guys up in Minnesota. Does a great job for us, man. I tell you, we have a great team. I don't want to get on a soapbox here, but it looks like we're maintaining the 72 people. But we have a great team. If you want to understand this more, get a hold of somebody at Harvey Performance. We'll walk you through it one-on-one. It's not a big deal. We'll take it in a scenario that you're actually using. We do this on a day-to-day basis, and we'll help support it. I make heat sinks. Okay, if you make heat sinks, Corey, are those heat sinks aluminum? We'll see if Corey's going to respond because he says he makes heat sinks. I'm assuming aluminum heat sinks, a little bit deeper, slots, thin walls. Could be, we'll wait for Corey to get back, but he says he makes heat sinks. We have a lot of solutions for heat sinks. If they are aluminum, we have a high feed mill for aluminum for heat sinks. And these things, use a high feed mill for heat sinks because you can go a lot deeper and you're not going to put any deflection on that wall. I have run our aluminum high feed mill going down 12 times D with a 20 thou blade, and I maintain 5/10 on every one of them with our aluminum high feed mills. We actually designed it exactly for heat sinks. I was involved in that. So yes, Corey, if you're making heat sinks, try that aluminum high feed mill. It'll be the only tool you thought you didn't need until you got it, and you'll use it all the time. So that's what I would use. It's a 2-flute aluminum high feed mill. Great tool for that. So the high feed geometry is for maximum cutting and high chip removal. That's what it's special comparatively. That's what makes it special compared. It is. It's what it does. It's all axial force. So a lot of the number one failure on a standard end mill is the radial deflection, right? The deeper you go axial is you have radial deflection. When that tool deflects, the tool wants to break, it wants to chip, it wants to bounce. So the number one thing with a high feed mill is all the forces are axial, okay? So they're axial forces, so you don't get the radial deflection. So now you're cutting on the bottom. You can't run as fast because your material removal, your MRR, let's just use it as an example. Let's say we got a 1/2 inch. This is a great example. Let's say we got a 1/2 inch high feed mill and we're going to run 500 surface foot. And ours are 5 flutes. Now I know a 1/2 inch high feed mill, and we'll just use a standard 316. Our 1/2 inch high feed mill, that thing is going to run 14 thou inch per tooth. 14. Yes, 14 thou. Now, here's what I'm going to do. My axial is only going to be not to exceed 5% of that diameter, right? So now our axial can only be 25 thou, but our radial can be 60%. So we can be up, let's say 280 here. Now look at our MRR. Our MRR is 1.87 on that tool, 1.87. Now, that's not setting any records for 316, 304. That's not setting any records. But this tool at a 25 radial will probably go down 5-6 times that diameter without deflecting. And that's the benefit of a high feed mill. You take a standard end mill that cuts on the side and go down 6-7 times its diameter, axial starts coming in and we start having issues. That's where you want to use a high feed mill. Hopefully that answers your question. What a great video so far. I'm catching up now. There's always one crazy guy in a shop. Yeah, it's true. Can't find them though. That's great. Great question. But manufacturing heat sinks features, do you make finished passes with a standard end mill after roughing high feed mill? Okay, so you're talking against the wall. So first of all, it all depends on, I think what the question might be is, if you're doing a heat sink because you're taking light, is the witness marks on the wall an issue? Well, in some heat sinks I've been associated with, it leaves a nice enough finish that they don't have to go back and clean up the wall. But if you do have to go back and clean up the wall, obviously there's geometry for finishing. You're taking a lighter radial. Remember, once our axial gets deeper, our radial gets lighter. It has to. It has. Let me take that back. It doesn't have to, but if you don't want to buy a bunch of end mills, it has to. I don't know. I'm trying to be political in my answer on this, but you want to start looking at your radial as your axial goes up. Remember, if we go over here to axial and I say I'm bringing my axial up, look at my radial right away. It tells me that that has to go down. How much? It's a guide, but you got to go in that direction to get the tool life up. That's what this chart is actually helping you with. Reese says, please expand further on Siva's question. If we use the more number of flutes and due to more feed rate achieved, but it will spoil the chip evacuation. So great question. So as flute count goes up, let's use this for that. That's a great question, Reese. We'll expand on that. So let's go to flute count and we go flute count up. I want to make sure I'm not lying to anybody. So as the flute count goes up, look at what it says to the radial. The radial has to go down because the more flutes we put in a tool, the harder it is to get the chips out. Now I'm going to give you, here's bonus material. I'm going to give you bonus material. The harder it is to get the chips out, the faster we spin it. Let me explain, okay? This is experience. We're talking experience here. I don't science, theory, whatever. I'm talking experience. When you have more flutes and you want to get a little bit more on the radial, be mindful not to jack the surface foot and spin that tool that fast. Believe it or not, centrifugal force, you will hold on to a chip the faster you're spinning. If you go a little bit slower, it's a little bit easier to get the chip out. So here's a solution. If you're having problems getting chips out, try bringing your RPM down. I would side more with a higher inch per tooth than I would side with a higher RPM. When I say RPM, Surface foot is calculated right here. RPM equals surface foot times 3.82 divided by diameter. That's your RPM, which is all in this calculator. Hopefully, Reese, that makes a little bit more sense. But the higher your flute count goes up, well, I just moved that out of the way. The higher your flute count goes up, the higher our axial can go. Because remember, see how the axial is green? So we could take this up higher because more flutes, bigger core, less deflection. All right. Somebody's asked the question, where does 3.82 come from, Don? Reese Trotter, thank you for being on here. Would you like to explain where 3.82 comes from? Because I've been doing this for 37 years, and I'm sure it's a pi calculation to figure out. But I'm a spreadsheet guy. Reese Trotter is one of our brainiacs. He probably knows where. Well, let me rephrase that. Reese Trotter is probably on Chat GPT right now, asking where the 3.82 comes from, because he's a younger guy, so he's probably chatting it up. But that's a great question. I'd be honest with you. It's obviously from the rotation of the diameter. It's a pi calculation. I'm sure Reese is going to find that out by every revolution that it actually comes. Circumference. Yeah, thank you, Swiss machinist. You're right. The circumference of the tool that has to do that. But listen, if you work with me, I ain't gonna lie to you. I don't know where 3.2 comes from. I could BS you, but that's not what these are about. This is not what any of my trainings are about. This is about experience, how I've worked at the spindle. I've been doing this for 37 years. Design tools, sometimes break tools by using this, and we have to figure it out. And that's where we learn, and that's where we understand things. Busted machining, like the name busted machining. All right, 16 times. All right, Jared says 16 times. What's Jared asking? Doesn't the heat come from? Okay, no. Doesn't the heat become a problem when you have more flutes? It depends on your radial. I mean, that's a great question. Heat does not become a problem with more flutes. That is not directly related to more flutes. Okay, so let me even see if surface foot goes up. It's not even in the flutes. So heat is basically from your chip load and your radial. That's what you're looking for from the heat. Okay, Jared. Okay, good answer. Okay, I'm trying to go through a lot of these counts. I love the interaction. This is what this is about. Hopefully everybody's enjoying this. We can do a lot more of these. We can dive into a little bit more specifics on cutting tools. But these are all great questions, folks. Really, really great questions. How about this? Whoever gives me the next great question is going to get what I think is a great question. Is going to get a helical polo. All right, fire them up. All right, fire one up. And it's not Reese or Mitch. We're giving away a helical polo right now to the next best question that we can use some of this MRR triangle on. What's Don's favorite color? Actually, the funniest thing is, that's a good question. I don't know if it deserves a polo, but I like dark colors. Dark colors, pretty much. 16 time deflection for twice the stick out. Thanks. Are you asking 16 times deflection for twice the stick out? You probably watched the last one where as the diameter gets larger, we start doubling the deflection as 16 times more deflection when we're twice the stick out, which means if our tool is hanging out of the holder a ½ inch and we extend it to 1 inch, you're going to get roughly about 16 times more deflection. That's the calculation on that as far as that goes. So if that's your question, that's a great question because it's in one of the videos. Is the crazy guy in the room with you now? He is. He's right over there. Wait a minute. No, I'm not. Yes, I am. No, I'm not. Okay, wait a minute. Hold on. So does MRR apply to solid end mills mostly, or are indexable included fully? I'm going to give that. That's the winner of the polo right there. I think it's Canadian V1. So for everybody out there, does the MRR apply to solid end mills mostly, or are indexables included? Indexables are included. That's 100%. When you're taking a radial step over an indexable, because that's what it is, a face mill, any kind of mill for facing, not even, I mean, some of the bigger mills, I wouldn't even call them face mills because they remove material. So you have a radial, you have an axial, and you have an inch per minute. Okay. Those three things are the factors. So 100%, all of those are included in the MRR triangle. 100%. How would all this play out with a blended profile of bronze and FRP material with interrupted cuts? Okay, so FRP, fiber reinforced plastic, and bronze, not mixed together, I'm guessing, right? Profile bronze and maybe mixed together with a little bit of bronze in there. Would all this play out with blended? It would play out the same way. If you're using the MRR triangle, doesn't matter if you're cutting composites, doesn't matter if you're cutting non-ferrous materials as bronze, copper, things like that, fiber reinforced plastics, carbon reinforced plastic. Doesn't matter. The MRR triangle applies because you're using these three things when you're using any kind of end mill. I don't care if it's 1 flute, 2 flutes, 3, 5, 7, 8. You have a radial, you have an axial, and you have a feed. Those things come into play any material that you're actually cutting. Do a good coating can solve heating issues. 100%. Coatings have a lot to do when you're cutting super alloys, ferrous materials, harder materials. It's no different than, I saw somebody who was from Canada. I'm from Chicago. It is no different than putting a coat on when you go outside. Your skin is going to get wore, just like the end mill. A coating, a good coating, a recommended coating that's for that material is number one. You really want to make sure you have a good coating on that. And if you're not sure what coating to use, most tools in our catalog are material specific. Pick the material that you're actually cutting, and we'll probably have the right coating on that material ASAP. No, I'm saying thanks to Jar. Okay, all the feet. My eyes are bad, can you tell? All right, so we got, so he was answering question above. Machinist, long cycle times, very long cycle times, 48 plus. So I think everybody's having a side conversation, which is great. That's incredible. Conferences diameter plus PI, which is in inches, and will need to be converted to feet for surface split. 3.82 is 12 divided by. Okay, there you go. There's your answer. Busted machining. Busted machining. What hat do you want? Helical Harvey? Micro or Valor? Oh man, somebody's got to take a Valor hat. Look at these things. Look at these hats. Valor Hole Making. That's another one of our brands. We created this, all manufactured in Gorham, Maine. If you have not tried a Valor drill, get a hold of somebody. Try one. Just try one. We'll send you one. Just try it. See how it works. I like Valor. Jared, thank you. Valor's a great brand, created by us with our engineers in the helical manufacturing facility. Understand, all of the Valor stuff is made in the helical manufacturing facility. It's not outsourced. It's not made anywhere else. All the coating, everything's done right there in the helical manufacturing facility. I'm a tooling engineer at Toyota. Recoat with Thailand, titanium aluminum nitride for cast iron and steels. Is there a better coating to increase MRR? There's a lot of better. I say better coating. Thailand's good because Thailand's 50% aluminum, 50% titanium mix as far as that goes. Titanium aluminum, which is that way. Altin's different. Altin's more aluminum, less titanium. That's the difference between Altin and TIALN. I am not a coating expert, but I'm going to tell you, Philip, that there are better coatings. The technology has gotten great. TIALN is an older technology. So there are better ones. We could probably help point you in the right direction if we need to, if you give us a little bit more specifics. Okay, wait a minute here. Okay, for so cast iron steel T plus coating. I'm sorry, that's a better answer. So yes, T plus I would recommend for ours. Even our A plus is better than Thailand. Titanium aluminum nitride is really good for drills, not so much for end mills. You want to look at more of an Altin to start with, because it has a higher aluminum content. So an Altan would be good, or an A+ coating, or a T+. So yes, absolutely, for cast iron. Very abrasive. Cast iron is very abrasive steel. So yep, that's what I would recommend. And that will increase your MRR 100%. You can start moving these numbers up. What you could probably do when you go with a coating, what's affected with a better coating is your surface foot. Surface foot needs to go up. So if we take this and we jack this up to 600 because we're running 500, look at what happens to our MRR. Our MRR goes up. I want to bring this to a reasonable number just so we can look at numbers. So if we're at 500, let's say we were running 500 surface foot, you're at 20.06 cubes, cubic inches per minute. Now, if you put a better coating on it, let's say we can go up to 600, you just went to 24 cubes, almost 5 cubes higher on that. So yes. What about an MRR optimization with small batches? You always want to optimize. Absolutely, 100%. I mean, you want to optimize in small batches with more tool life than maybe MRR, right? You want to make sure you're getting the life out of the tools. But yeah, a 100% small batches, if you're calling 3-5 batches of what you're running, you definitely always want to be looking at your MRR, because I had my own machine shop for years. It's all quoted time, right? It's all quoted time. You make the profit on your parts based on how quick you can get it done, how few consumables you use, and how quick you get it out of the door. Now, let me give you a variable there. Maybe machine time is the issue and MRR is not. So you could sacrifice tool life by increasing MRR, but you gain machine time. You understand that? So it's not always like, well, I want 3 hours of tool life at 20 cubes. Maybe you can get away with 2 hours of tool life at 40 cubes, because now you cut your cycle time down, that part gets out, you're a little bit more profitable. So it all determines what's most important to the team, what you're trying to do. If it's about machine time, you got to get it off the machine. So maybe that $50, $100 end mill in the scheme of things is only 50 cents in that part. So is that what you really need to be focused on? Is that 50 cents? Or would you rather have that machine time up and running for the next job? That's always a judgment call that you need to make. Does heat leaving with the chip matter more for high temp alloys like titanium? 100%. 100%. But Reese, titanium Inconels, they don't like to take heat. So getting the heat into the chip in titaniums, Inconels, Hastelloys is a lot more of a difficult feat than it is with steels. So yes, you want to, and where does that come from, Reese? It comes from surface foot. Having the optimal surface foot to plasticize the chip so you can remove it without doing damage to your material and to do damage with the end mill is key. Where do you get the surface foot recommended? Well, you get them from MAP, you get them from your machine tool dealer. You get them from that. That's what you want for recommended speeds and feeds. Let's see. I'm a field service technician. Often people blame the machine for issues they're having with tool deflection. What advice or resources I can perhaps pass along to said customers that may need help? So what I'm understanding the question is, people blame the machine for issues they're having with tool deflection. First of all, I don't know why that is, because you can tell right away with your diameter to stick out ratio where the deflection's coming from. The deflection probably is going to come from the cutting tool. It is. It's going to come, unless you have an old machine, but somebody pointing it at the machine and saying, hey, my machine's deflecting. If you can check the run out on the spindle prior to any tool being in there. You can check the run out on the holder before the tool's in there. And then obviously you can look at the tool. This is a great resource to kind of get back to your customers and basically say, well, there is a maximum rigidity on the tool based on the diameter sticking out of the holder. And that's key to make sure. But A machine that has low rigidity, are there machines with low rigidity? I don't know what you're a technician for, if it's a machine tool dealer or something like that. But if there's a machine with low, there are machines with lower rigidity than other ones. But I can't tell you other than dissecting what their tool path looks like, what their radial looks like, what their axial looks like, what their flute count and things like that. But if they're having deflection, have them start looking at flute count. Flute count might be a big thing. Maybe you need a bigger core, bigger tool, bigger diameter. That can always help. Philip, take a spring pass and see remove material and check machine backlash. There you go. Philip's helping. Hey, by the way, I don't know if you watch all my videos, but there are 3 guarantees in life, right? Death, taxes, and spring passes. Don't forget it. So those are the 3 guarantees. Swiss is less rigid than a milling machine. And not to mention 5-axis is a little bit different than 3. Keep that in mind. I mean, you can't really push a cutting tool on a 5-axis machine as much as you can on a 3. You have more axes, you have more ball screws, more things moving. You do lose a little bit of rigidity based on the machine. So there's a lot that you need to do as far as that goes. It's more RPMs, average out holder. Good stuff. Well, it looks like this is kind of winding down. Does anybody have any other questions or any other things that we can kind of discuss before we close this thing up? I'm going to stand back here now. Look at this, just like the, but then I can't read what anybody's asking. Have them hold a gallon of water close just for a minute, at arm's length for a minute, so they understand the force. Yeah, at the length, the stick out affects deflection. Good suggestions. I'm seeing all the application engineers on here. Let's get, I just want to close by letting everybody know this MRR Triangle is a tool that helps you understand a little bit better how things are working at the spindle. Hopefully the seminar training, YouTube Live helped everybody with that. We're going to post this stuff. We're going to send out these hats. Who wants to give away one more polo? Why don't we give away one more polo? What would be a good question for one more polo? Does anybody, let's see, how many flutes are recommended? How many flutes would you recommend in 6061 aluminum at 3 times diameter? What's your ramp angle? We're just going to do peripheral. Jared says 4, and okay, so I'm gonna take 2 people, Jared and Alizar, 4 and 3. Those are the first 2 answers. So Jared is getting a polo, and Alizar Diaz is getting a polo. There you go. 4 and 3. I would recommend it. Jared, here's why I love your answer, Jared, because there is nobody that I know of that has a 4 flute aluminum tool. They have 5s, they have 3s, they have 2s, and you can use a single flute. I've always thought that a 4 flute kind of cuts the middle between the 5 recent and the 3. So 4 flute aluminum tool, I like that answer. That's why Jared's going to get a polo, and Alizar Diaz is going to get a polo too as well. With that, yes, great. Pat is one of our moderators. He says, if your question wasn't answered during the live stream, we haven't forgot about you. We'll get your answers. So again, feel free to contact anybody at Harvey Performance. Feel free to contact anybody. Watch our YouTube videos. Ask a question in a YouTube video. I try to get to all those questions when I can. I apologize for not getting a new video out. The next video is going to be on coatings. I think somebody asked about coatings. So the next video will be on coatings. We're going to talk a little bit about what is coefficient of friction. What is oxidation temperature? How does the coating affect the tool? So these are things that we want to talk about. With that, I'm going to thank everybody that joined us today, everybody that came in, everybody that left, everybody that was giving us a thumbs up. And we appreciate your business. And if you have any questions, please feel free to contact anybody at Harvey Performance. Thank you, and have a great rest of your day and a great rest of your week. Bye, folks.